Hello everyone, I'm Yunzhe from Boston University. Here I'm going to talk about our work using a deep learning model to solve imaging through scattering problem, which is resilient to defocus across over 10 depths of field. In addition, we will make the neural network more interpretable to show that the trained network is able to encode the decorrelated speckle patterns into a set of representations that are highly informative and well correlated with the input object. Imaging through scattering medium has wide applications across many areas. The basic idea is to figure out the input by the normal measurement y and the input-output relation a. Different strategies will influence the hardware and data capture design, and both model-based approach and data-driven approach have been explored to solve the inverse scattering problem. The input-output relation A can be regarded as a transmission matrix, and within small memory effect region, it will be shift invariant. However, medium perturbations and the trade-off listed on the right are common problems for imaging through scattering. We will use learning-based method to make the network robust to those variations and interpretable. In our work, generalization can be achieved by designing the data acquisition strategy, and also to make the black box network interpretable, we will pick inside the network. Sufficient statistical variations are important for improving generalizability. Here we include two major variations. One is medium perturbation, another is defocus. We both consider diffuser shift and camera shift. Our previous work shows the learning-based method can be robust to medium perturbations, which you can have more details in the reference here. And for the current work, we took all these variations listed into consideration. The depth of field is defined by the axial speckle size. Using axial speckle pattern for autocorrelation, speckle size is its full width at half maximum of the curve. We chose 3 positions for 4 diffusers to train our network and tested on other positions. The result on the right shows both diffuser defocus and camera defocus. The network can make good predictions where defocus is ranging from 1 to 10 depths of field. When the defocus region becomes larger, like 10 depths of field, performance may decrease. We also quantitatively evaluate the result by Jacquard index for the 2 cases, which also shows that it's robust within extended depths of field. Next, I will talk about interpretability. All the data we have are high-dimensional data. Dimension reduction is crucial for interpreting and visualization. Here we are using a tool called UMAP to project high-dimensional data into 2D space. For our case, the display digits can be projected on this map where a single point represents an object figure. The same goes for the speckle patterns. You may notice that the objects are clustered by digit structure, but after going through diffusers, they cluster by different scattering situations, for example, different diffusers with certain positions, showing that statistically similar data forms a cluster, and raw speckle intensity encodes the medium or defocus specific information. After knowing the data we have, we then pick inside the black box during training. Encoder is used to extract the information, and decoder are just used for generating image using encoded information. So we extract the latent code at the bottleneck of the network for interpreting what's the information it encodes. During training, the input are clustered by different scattering situations. However, after encoding the information, the learned latent code are clustered by object structure, which shows that the encoder distills the object-specific information and disentangles medium or defocus information. Next, we will pick inside the network for prediction. When predicting, the input dataset are totally unseen and different from the training set, but our network still can encode the information and make them cluster by digit structure, which are the same as the learned manifold. Encoder can distill the object-specific information for different unseen cases, which shows generalizability. In summary, we made learning-based method more generalizable and improved the interpretability by dimension reduction. And at last, I want to thank my research group and NSF for the support. And thank you for watching the video.